Chapter 1, Part 7, Curved Arrow How-To and Resonance Continued. How to draw curved arrows. Curved arrows show the flow of electrons. Electrons always move from a place of high density, such as lone pairs on electronegative atoms, pi bonds, or negative charges, to places of low density, such as carbocations, positively charged species, or electropositive atoms. Curved arrows can be used to show the breaking of bonds and the formation of new bonds. Anytime you are drawing curved arrows to show either resonance forms or even a reaction mechanism, all structures must be proper Lewis structures. When you are drawing curved arrows to show resonance, you never move the nuclei of atoms. When you are drawing out mechanisms and using curved arrows, you can actually move a lot of things. Mechanisms show chemical reactions and they show chemical transformations. So you actually have to break sigma bonds and move the nuclei of atoms around in order to show that. Let's look at some examples of curved arrows in resonance. First up, we're going to look at benzene. Benzene is a molecule that has 6 carbons and 6 hydrogen atoms. And benzene can be drawn in 2 different ways. You can either show the double bond starting vertically on the left-hand side, or you can have it vertically on the right-hand side. These 2 molecules are the same. You can show their relationship via resonance, or you can rotate your paper 60 degrees, and it would be the same molecule, right? But we want to show how these are related through resonance. So if we were showing this in resonance, we would need to show how the pi bonds are moving around the ring and relocating. So these pi electrons here are able to move over here. The reason they are able to do that is that this carbon is sp2 hybridized, this carbon is sp2 hybridized, and so are all of these. And we're going to talk about hybridization a little more at the end of the chapter, but this is a really important key thing. You cannot move pi electrons towards an sp3 hybridized atom because there is no p orbital to move those electrons to. But as long as everything is sp2 hybridized, or if you have something that's sp hybridized, you can move pi electrons towards it. So in this example, I'm showing these pi electrons moving over one position. That's how they end up here. But again, like we saw in the previous video, this carbon currently already has 4 bonds. Remember, there is a hydrogen atom here that we did not draw and we do not need to draw. If I were to just put this double bond here without moving the other pi bond, that carbon would have 5 bonds and it would not be okay with that. So we're going to have to move this one as well. And when we do that, we are causing a domino effect because now this pi bond has to move over as well. So that is the relationship between these 2 molecules. Let me do a little bit of color coding here so you can kind of track what I'm saying. Now, the resonance hybrid for benzene is often drawn just as the 6 carbons in the hexagon with a big circle in the middle. The circle is indicating that each of those carbons is equally sharing the double bond. When we get to the chemistry of benzene in chapter 9, I'm going to ask you never to draw it this way just because I want you to be able to show the mechanisms that are happening in the reaction. And for that, you're going to need those pi electrons. In our next example, we have acetate. I want to show again, we have an sp2 hybridized carbon, which is why we are able to do the movement that we're about to do. So these 2 molecules are related through resonance, and the difference is that this oxygen ends up being connected via a double bond, and the existing double bond in our first structure breaks and turns into a single bond. So let's show how that happens using curved arrows. So curved arrows always start in an area of high electron density. In this case, this oxygen is negatively charged and it has 3 lone pairs. So we can take one of these lone pairs and we can use it to form a double bond. Notice that my arrow is pointing at the area between the oxygen and the carbon. That's how I'm showing that I'm taking those electrons and putting them here to make a new bond. If I had taken my arrow and pointed at the carbon, that would mean something different. And then at the same time, I also need to show this pi bond breaking and pushing electrons up onto the oxygen. That's where this extra lone pair that gives us our formal charge is going to come from. Now, looking at these resonance forms, you can see that either one of these oxygens could have the negative charge, and either one of them could be neutral. And they share the double bond equally. So we can update this resonance form with some partial negatives. Our resonance hybrid shows that these two oxygens are equivalent to each other. In our last example of resonance, we're going to look at ozone. Ozone is kind of a weird molecule because it has these 2 formal charges on it. Now notice the central atom never really changes as far as its bonding scheme. It always continues to be an oxygen that has 3 bonds, 1 lone pair, and a positive charge. What we are changing is that the oxygens on either end can be either the double bonded oxygen or the single bonded oxygen. And the singly bonded oxygen is going to have that negative charge. Now, just like with benzene, any of these resonance forms, because they have symmetry, could be just the same molecule but flipped over. In this case, if you were to take this molecule and flip it over like a pancake, it would look like this. And in fact, I'm pretty sure that's how I made this image because it's a perfect mirror image of the one on the left-hand side. But we're going to show how they're connected via resonance. So I'm going to take this lone pair and use it to make a double bond between these 2 oxygens. And that's where this double bond comes from. And then I need to break this double bond and put those electrons back onto the oxygen. That's why my arrow is starting at that at the pi electrons and pointing at my oxygen, because that's actually where my lone pair ends up, is on the oxygen atom. And in the resonance hybrid, you can see that the 2 oxygens on the end are being shown as equivalent to each other. Now let's look at some examples in reaction mechanisms. Some of these mechanisms may not make sense yet because we haven't gotten very far in organic chemistry, but I did use some acid-base examples which should look familiar from Gen Chem 2. Mechanisms show how a chemical transformation occurs, and therefore mechanism curved arrows often show the formation or the breaking of bonds. In this first example, I just have hydride attacking a proton to make water. This is a reaction that you saw over and over in Gen Chem 2 anytime you were doing an acid-base titration. So in this example, hydroxide has a negative charge and the proton is positive. There's kind of a very simple rule in chemistry, which is that minus likes positive. Minus will always attack something positive, and that attack will look like the formation of a bond through the donation of electrons. So one of these pairs of electrons can be used to make a bond to hydrogen. So notice my arrow is starting over on my electron pair and it's pointing to the hydrogen because I'm actually using it to make this covalent bond. So those electrons end up in that covalent bond. So curved arrows actually mean something, and that's why it's going to be so important that you start and end in the correct place. And when you're working on our homework platform, Achieve is going to be almost obnoxiously picky. And the reason it's being picky is that you're probably doing something that's technically not right. You're either not starting in the right place or you're pointing to the atom next door to the bond that you were trying to actually point to. So Achieve is going to be very picky because it wants you to be right. In this example, we are also doing an acid-base reaction. This time I have hydroxide reacting with acetic acid. This is just like the vinegar titration that you would have done in the Gen Chem 2 lab. So in this one, you can see the difference in the reaction products here. We are actually reacting with this acidic proton. So what's happening here is, again, hydroxide is attacking this hydrogen. Now, I'm making a bond between that oxygen and that hydrogen. Hydrogen can only make one bond. So in order to allow this to happen, I also have to break my bond between the oxygen and the hydrogen by giving those electrons back to the oxygen. So that's where this lone pair on our acetate anion is coming from. And then our covalent bond in our water molecule came from this attack. So every arrow means something, and it shows the flow of electrons. Chemistry always starts with electrons. Electrons are what actually make chemistry happen. So your arrows should always reflect that. One more example. This one is significantly above where we are right now. This is an example that I believe won't pop up until chapter 13 or so. So in this example, we have something that's very obviously negative. This is going to be the source of our electrons. And where it's going to attack is over here. And the reason it's going to be interested in that carbon is because this bond is polarized. There's a partial negative on our oxygen and a partial positive on the carbon. So that's why it's going to be interested in that carbon. Oops. Okay. So our cyanide anion attacks here. This carbon already has 4 bonds. So in order to allow this attack, we're going to have to break this pi bond and push some electrons up onto the oxygen. So that's where one of these lone pairs comes from. And notice we have formed a covalent bond between the carbon that's here and the carbon that's part of cyanide. So why is resonance important? I kind of tried to mention this at the end of the last video, but we're going to spend a little more time on it now. Resonance stabilizes a molecule. The distribution of charge across multiple atoms shares the burden of the charge. It's something that we just have to remember is that atoms do not like to carry a charge. So even though, for example, oxygen is electronegative, it doesn't want to be negatively charged. It just wants to hog the electrons in its covalent bond. But it doesn't want to actually have a charge. A charge means that you are carrying more or less electrons than you really wanted to. So think of it like trying to carry something heavy up the stairs. Oxygen doesn't really want to do that, but it'd be a lot nicer if someone else came along and helped carry that heavy item up the stairs. And that's what resonance does. So for example, we saw with benzene, this is kind of a fun fact here. Benzene is super, super stable. It's actually very difficult to get benzene to do chemistry. You have to kind of manipulate it with some interesting catalysts. And what makes benzene so stable is that it has these 2 resonance forms that are equivalent to each other. So again, when this pi bond is able to move here, and this one is able to move here, this one is able to move here, we're basically just saying that all of these carbons are equally sharing that double bond and the single bond. So they are all identical to each other. There is no excess of electrons on any one of these carbons in the benzene ring. They are all equally sharing the burden of those pi electrons. Now, when we have more than one resonance structure, it can be kind of difficult to know which one contributes more. Sometimes it's really obvious. In this example that you're about to see, I think it's kind of obvious. We have a resonance form here where the pi electrons in the double bond are able to move up onto the oxygen. And when it does that, it creates this resonance form. So those electrons now live on the oxygen. And by doing that, we've created a positive charge and a negative charge out of a molecule that was previously neutral. So let's look at some factors that can help us decide which one is more important. So rule number one, the more covalent bonds you have, the more stable a molecule is. Looking at molecule A, we have 1, 2, 3, 4 covalent bonds. Molecule B has 1, 2, 3 covalent bonds. So that's going to be a point for molecule A. Anytime that you have charge separation, that's going to decrease stability. This is creating opposite charges out of a neutral molecule. Basically, we have a positive and a negative on neighboring atoms. This is like having two magnets next to each other and telling them, hey, you can't react with each other. You have to stay apart. They would much rather click together and make that double bond than to be apart as a positive and a negative. So that's going to be a point for molecule A. And then rule number 3, structures are more stable when each atom has a complete valence shell. In other words, when the octet rule is fulfilled for every single atom. So let's look at molecule A. This oxygen has 2, 4, 6, 8 electrons around it. Carbon has 4 bonds, right? 1, 2, 3, 4. That's 8 electrons. And our hydrogens don't need a full octet. So that's a point for molecule A. It does have a complete valence shell on every atom. And then for molecule B, our oxygen has 1, 2, 3, 4, right? Or sorry, 8 total electrons. So that's good for oxygen. But the carbon only has 1, 2, 3 bonds. That's 6 electrons. Molecule B does not have a complete valence shell on every molecule. So molecule A wins pretty handily.